All right, shall we get started? Okay, so I'll finish the determinant stuff. I still owe you the big formula today, and hopefully we'll get to eigenvectors and eigenvalues, which is going to be the basis for much of the next stuff we are going to cover here. Oh, one organizational thing. I think I'm going to just scratch the difference between homework and projects, because I would like to probably do more projects than homework, and then I don't want the few homework to be more important than the project, because that would be silly. I guess I'll just lump it all together, if that's okay with you. Seems reasonable. My thinking was that the homework will be like this, sort of like a theory type questions like you have in the midterm, but I think the projects are actually much more interesting and important for you, so I guess I would want to do more projects. Sounds good. Okay, so determinant. So let's quickly recall what is determinant. So the first thing which you just must remember is that a determinant is a function that takes an n by n matrix, so it's always a square matrix, and gives me a number, right? And I think I was explaining how this single number characterizes the matrix really well, right? Before we get there, we need to recall how the determinant is actually defined, or even before defined, how it's denoted, right? So either with this dat or with these vertical bars, which you can easily confuse with like the notation for the matrix, right? Which is like usually some matrix here. But this already means apply the determinant function to it. And these were the three defining properties. We said the determinant is defined as having value 1 on identity. And if you exchange two rows of a matrix, you change the sign of the determinant, and the determinant is linear with respect to each row. And I told you, very careful about this linear. That doesn't mean that determinant would be a linear function. That case wouldn't really be very interesting. We discussed it the last time, right? So remember this. What this linearity really means. It's linear in the sense that we can separate, we can write it that we can just take like a sum of two vectors, and we can split it into two determinants. In that sense, it is linear. Okay, so from these three defining properties, what we did, we derived lots of properties that logically follow from them. So there was these properties like if determinant has, if the matrix has two rows which are identical, then the determinant will be 0, right? The most important properties I would like you to definitely remember is this one. That's what we sort of ended the discussion of all the elementary transformations and so on. So that's saying that the determinant of a product of two matrices is the same as the product of the determinants of the two matrices. And here goes without saying that they both must be square and they must have the same dimension, right? If it wasn't, the determinants wouldn't even be defined, okay? Keep that in mind. And the other super important thing, which I would also like you to remember, is that the determinant of a matrix is 0 if and only if the matrix is singular. Because that's a hugely useful thing. That's if you can quickly compute a determinant, you can quickly check if the matrix is singular or invertible. Okay, and I also told you what is the determinant of a 2 by 2 matrix, right? This is something that's easy to remember. But I guess the rule, I don't know if you remember this rule. The rule is like you sort of walk on the main diagonal and then on the opposite diagonal, and on the opposite diagonal you go with minus. That's how you can remember the ADBC. So you go on the main diagonal and then on the off diagonal, or I guess how's it called? The reverse, the opposite. Let's call it the opposite diagonal. I don't know what's the right terminology there. For 3 by 3, this rule actually still applies. So that's like a useful thing if you want to just remember the 6 terms in the 3 by 3 determinant case, right? So think about it this way. So I walk like this, okay? So the first term is going to be A, E, I. Then I do the same thing starting from here. So I go B, F, and then I run out of the matrix. Do you see what I'm saying? It's not as sharp as I would want it to be. Maybe a little bit better, huh? So here I go BF, then I run out. So instead I wrap on the other side of the matrix. Do you see that? So I will get BFG. One, step to the right, and down. So I overflow and I have to do the G instead. And here if I do the same thing from C, so I'll start with C, then I already overflow to D, and then H. Okay, see that? So that's like, I don't know how to depict it graphically. And then we go in the other direction. So we start from, and we put these with minus. So we do C, E, G. So that's starting from C and then going left and low, left down, toof, 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 C, E, G. Then I do the same from F, for example, F, H, A. So again, toof, toof, and here I overflow. If you like know computing with modular, then you are, then you can relate to this quite easily. And the last one would be I, B, D. Okay. So if you remember this trick to it, then it's very easy to remember the determinant of a 3x3 matrix. I don't think you really need to remember it, but it can hurt. But I will explain you in a little bit that the determinant of a 3x3 matrix is immediately useful. For example, it gives you the formula for the volume of a tetrahedron. So we will get there. The determinants are incredibly useful. Okay, so what I owe you is the big formula, right? So how this generalizes to an n by n matrix, and that's what the big formula does, okay? So we already realized, I guess if I put there like the silly case of a 1 by 1 matrix, which equals its own determinant. See, that's why I don't like this notation so much, because this looks like an absolute value, but it's not an absolute. This means determinant of A. Okay. So we already established this has one term, this has two terms, AD and BC. This has 6 terms, so it grows as n factorial, right? And indeed, for an n by n matrix, so here we work on A, which is an n by n matrix. So here we will need to look at permutations. So let's talk a little bit about permutations first. So first of all, I guess, what is a permutation? So I will give you a definition. Permutation is a function from integers 1 to n, mapping them to integers 1 to n to themselves, which is bijective. Do you know this terminology, bijective? It's also called one-to-one mapping. So what that means, it's actually quite simple. Let me give you an example for n equal 3. So for example, a function that maps 1 onto 2, 2 onto 1, and 3 onto itself, that's a perfectly valid permutation, right? If I did, for example, like p tilde 1 mapping to 1, then p tilde 2 was mapping also to 1, and p tilde 3 was mapping to 3, would that be a permutation? No, it wouldn't, because it wouldn't be 1 to 1, right? So this is not a permutation, this is a valid permutation. You understand what means 1 to 1 mapping? Okay, good. So we talked about permutations a little bit before, and I said that they can be represented using matrices, right? Even more, there is even more to it, that they form a group, and you can reason about all these group properties. And so here the matrix representing the permutation would be, so I guess capital P matrix would be like this. It would be 0, 1, 0, 1, 0, 0, 0, 0, 1, right? It sort of makes sense, because then if you apply vector to it, if you apply x, y, z vector to it, then this P matrix just flips, just basically performs the permutation on the coordinates, right? So basically this just means that the first row gets the 1 in the second column, the second row gets 1 in the first column, and the third one in the third column. So just very obvious one-to-one mapping between permutations and permutation matrices. Remember we talked about permutation matrices before. I told you that they are binary matrices such that on every row or column there is exactly 1, 1 somewhere. Okay? Now the important thing I will need to write down the big formula is that every permutation has a sign. Sign of a permutation. Do you know what that is? It's typically called like function like this. And what all that means is, so I guess I should have started by saying that identity is also a perfectly valid permutation, right? P1 going to 1, P2 going to 2, P3 going to 3, P4 going to 4, and so on. Identity is perfectly valid. It's a trivial permutation, but it's certainly 1 to 1, right? So the sign of a permutation can be either +1 or -1. And it's +1 if we can get it from identity with an odd number of swaps. So odd number of exchanges. Let me just write swaps because it's faster. And -1 would be if it's, oh wait, odd should be -1, sorry, exchange. It should be, this is even, and -1 if it's odd number of exchanges. So what do I mean by if I start with 1, 2, 3 with the identity permutation, then I flip, then I do one exchange, I do 2, 1, 3, I get this permutation, and because it's odd number, one swap, that has sign -1. Okay? If I do another one, for example, if I did, what could I do? Well, whatever, right? Like for example, this one. So this one would have sign. So the identity has sign 1, this has sign -1, this has sign 1, and so on. Do you know what this sign of a permutation is in terms of the matrix? If I represent the permutation using a matrix, what do you think the sign of a permutation becomes? Correct, or you can say just the determinant. But you can certainly say sign of the determinant too, because determinant, this is an orthonormal matrix. I think we didn't have that yet, but it's true that orthonormal matrices have determinant only plus or minus 1. And that's the first defining property we, second actually, that if we exchange two rows of a matrix, you change the sign of the determinant, right? So it's exactly the same idea expressed in matrices, okay? So the determinant, so the sign of a permutation is the determinant of the corresponding permutation matrix, okay? And with this setup, I can write the big formula. So for if A is an n by n matrix, put it again here, then the formula sums over all permutations. So P is one permutation, and this capital or calligraphic P is the set of all permutations on numbers going from 1 to n, on integers 1, 2, 3, 4, 5, and so on till n, okay? Here I have the sign of the permutation, and here I have a product of, let me first write it and then I will comment on it. So those are elements of the matrix A, okay? And this means that the first index just goes over all rows, and the second index applies the permutation and picks the corresponding column. Do you see what's going on there? So I go over all permutations, and I always do a product of n elements of the matrix. And which elements do I pick? That's what the permutation decides, okay? And I have to multiply, all these are multiplications, just scalar multiplications, right? I have to multiply by the sign. So if you want, you can, like here on the 2 by 2 case, it's trivial to work out that this indeed is equivalent to this in the 2 by 2 case. Because on 2 by 2, what permutations do we have, right? We have 1, 2, the identity permutations, and it's 2, 1. So the sign of this one is +1, the sign of this one is -1, right? And this the identity certainly gives me A and D here. A1, 1, A2, 2, right? And the second one gives me A1, 2, and A2, 1. And it has sign -1. Is that clear, or shall I work it in more detail? It's sort of silly. I'm just arguing that for n equal 2, this formula reduces to exactly this. And for n equal 3, this formula would reduce to exactly this. And for n equal 4, you could work it out. You would have 24 terms there, right? Because here we have the number of all permutations on a set of a diamond of size n is n factorial. So it's good to know this formula. It's sometimes useful. It's mostly useful for small matrices when n is small. But I guess the important thing to realize that what the determinant is, it's always just a product of n numbers. I guess, yeah, always product of n numbers taken from the matrix times the sign of the permutation. Okay, any questions to this? This is the big formula here. Okay, so if that's okay, then I will move on to determinant and area. I will give you the geometric interpretation of determinant. As I started with during the first lectures, I was saying that it's sort of cool to relate these algebraic concepts to geometric things. You know, let me see this chair would work. Does it really? Determinant and area. So by area, I mean that we are now, well, I'm gonna first work it out in 2D. So let's look at 2D matrices. So our good friends 2x2 matrices. Okay. And basically, I want to convince you that determinant is very closely related to area. I guess the first argument I can give you is what are actually the units. If we like imagine we are in physics, and our vectors or the coordinates of our vectors have some actual physical units, meters or feet or miles, or whatever units you prefer. That doesn't matter what particular unit you pick. What actually matters is how the determinant scales. Okay, so let me call A2 like a 2x2 matrix. So let's take a matrix which has just two vectors in it, and it's a 2x2 matrix. So that's why there's a little 2 here. So what do I mean? How does it scale? So if I change my units from meters to feet or something like that, that's you have to do a lot if you travel to Europe or some place non-US. So that what it means that the change of units just means that you multiply each of the vectors by some t, right? So you do a matrix like this, right? Now, how does the determinant change? That's sort of easy. So this matrix is determinant A2. Then this matrix, the determinant of this matrix will be how much? I think we had it last time. 2 squared, the determinant of the original matrix, right? And that's quite promising, right? This t squared tells you that this really relates somehow to area, right? Because think about it. So if something scales with square, so for example, if I have like a square here and I'm measuring its area, if I multiply the units by t, let's imagine that t is 2, okay? And if I multiply the units like this, then what do I get? I get bigger square, right? This bigger square has 4 times bigger area, right? So that's because 2 to the power of 2 is 4, right? You could just say that if the units here are in meters, then here you get meters squared, which are just units of area. But I just don't want to use any particular unit. I just want to give like this scaling argument, right? And of course, in 3D, here we will get t to 3. In general, if you had a matrix, n by n matrix, square, always square. So the determinant of TA is, of course, t to n determinant of A. So specifically in 3D would be t to the power of 3, which means that indeed those are units of volume. Okay. Okay, so units is one thing, and the other thing is what exactly the determinant means geometrically. So let's take a look at that here. It's quite cool. So we are still in 2D. So we are in R2. And let's pick some 2 vectors. Let's pick a vector, for example, like this, and another guy like this. Let's say that this is a vector v1 with coordinates x1, y1, and this will be v2, coordinates x2, y2. I really like some better chair. So what's going to be the determinant of a matrix such that the matrix has these vectors v1? Let me do it slowly. Which is the determinant of x1, y1, x2, y2. Okay. Well, we know the formula, right? In 2 by 2 is that simple, x2, y1, right? And let me now try to give this a geometric interpretation. Okay. I want to ultimately relate it to area. So, okay, this is unfortunate, but the determinant, you can notice I can write it in this way. I can write it like x1, y1, that's the first vector, transposed x2, y2. So, except that this is not true. Okay, let me do this again. Let me do this nicely. So this is my v1 and v2. This is x1, y1, transpose, and here I will have, let's do it like this, y2 and minus x1. Now this is actually correct. I got a little bit too happy. I need to be a little bit careful. I can write this as a dot product of these two special vectors. I mean, the first one is just the v1, right? It's not too special. And what is the v2? Well, I just put there the value, so I get the same. I get the determinant. Do you see that the dot product is indeed the same as this, right? It's x1, y2, that's this term, plus y1, x1. Wait a second, did I do it wrong? This, of course, this should be x2. Sorry, I don't know what I'm doing. Okay, now that's correct. Okay, so this is x1, y2. That's what I have here, and it's minus x2, y1. Yeah, now that's correct. So the determinant is a dot product of these two vectors. Okay, the first vector, that's my v1, and the second one, what is the second one? Let's think about it for a second. Well, it's something that came from v2, right? It's almost v2, right? So what is it specifically? Well, I can get it from v2 by applying this matrix, right? So if I take my v2, which is x2, y2, apply this matrix, that gives me exactly the one I actually want there, y2x minus x2, okay? Which me, for some reason, I'm doing lots of mistakes today. What is this matrix? Yes, that's a rotation. About what angle? 90. Correct. And in what direction? That's actually important, right? Let's write the. This is a general rotation. By default, we are using our usual right-handed coordinate system. That's our convention, right? So we have x here and y here if we are in 2D. So for what theta will I get exactly this matrix? Negative 90, that's right. Yeah, so this is exactly like a rotation for negative 90. So what it means, it's a rotation by 90 degrees clockwise, right? Because if this angle was positive, it would be counterclockwise. But I have negative angle, so it's rotating clockwise. Okay? So yeah, so this mysterious second vector there is just 90 degrees clockwise rotation of v2. Okay, so let me call it v2 rot, where the rot means like rotated 90 degrees clockwise. Okay, and let's see what that means. That's because that's quite interesting. So if I rotate the v2 counterclockwise 90 degrees, I think I'll get something like this, right? So this will be my v2 rot, rotated. And here, this is just, let me write it in terms of the v's, v2 rotated, Okay, so that's a dot product of these two vectors, right? Well, we know what the dot product is, right? We know, so let me write it again here. So determinant of this matrix V1, V2 is this dot product. And we know this formula for dot product, right? This is the length of V1. This is the length of V2 rod. And here would have a cosine of the angle between the two vectors. That means this angle. Okay. So now what does this mean? Or what means, let's see, V1 cosine alpha. What is V1 cosine alpha on this picture? Geometrically. And what I'm trying to do here is to give a geometric interpretation to determinant in 2D. So length of V1, well, that's this length, right? Times the cosine of alpha. What that's gonna give me? Exactly. So perpendicular projection onto V2, right? So the length, let me note like this. So this length would be h, and that's the projection of V1 onto V2 rod, which is the V1 times the length of V1, the norm of V1 times cosine alpha. So let's call it h, for example. So that means that what we have here is W2 rod times h, right? But the W2 rod, that's just a rotated, V2, sorry, what I'm saying. V2 rotated is just rotated V2, right? So we know that rotation does not change the norm, right? So this is equal to the norm of V2 times h, okay? And what that is geometrically, well, look at this picture. This is the length of V2, right? That's the length of this vector. H is this. Okay, so what is the norm of V2 times h geometrically? Area of something, right? Well, yeah, even ultimately it will be a polarigon. That's what I'm trying to get to, right? But it's first you can notice it's an area of this rectangle, right? This rectangle here, this is the length of V2, right? This is h. So this determinant is actually equal to the area of this rectangle, okay? And here you can get to the parallelogram. You can play the following trick. You can chop this triangle here, and you can paste it here instead. So you know what? Let me do it on a different picture. So this is my rectangle. Here I have a little triangle. So here I can chop it over here, and I can instead paste it here, okay? If I do that, of course, the area does not change, because I just chopped the triangle and put it somewhere else. And then this is exactly the parallelogram. So this is my V1, and this is the V2, okay? So this is parallelogram defined by V1 and V2. So parallelogram is sort of a funny word. What it means is just a skewed rectangle. And that's what determinant is. That's the area of the skewed rectangle defined by V1 and V2. Okay. There is one, it's actually not true what I said. There is one little catch to it. Before we go to the catch, we can just say that you can sort of intuitively see how does it relate to determinant. So if I am bringing the V1 and V2 closer together, oh sorry, this was supposed to be V2, this was supposed to be V1, right? If I bring them close together so they have like a small angle between them, then the determinant is going to be smaller and smaller, right? Because I'm reducing the area. In the extreme case where they are collinear, where V2 is just a multiple of V1, so that means that V2 is just alpha times V1. What happens to the determinant? We will get a determinant of what? Of V1 and alpha V1, right? That is 0. Why is it 0? Well, it's obvious from the geometric interpretation right now. That's why the geometry is useful, right? Of course, the area of this is nothing, right? It's 0. It's not a good idea to use things like this in like finite elements or something like this, because if you divide by the area, you divide by 0 here. It's just a quick aside. Why is this determinant 0? I have a column v1 and another column which is alpha v1. I guess that's simple, right? This is, I can take the alpha out of it because we know that this is just a multiple of a column, and I have determinant where 2 columns are the same. I told you before that all the rules for rows automatically transpose to equivalent rules for columns. So if I have a determinant which has 2 columns which are equal, well, that's 0, right? So the entire determinant is 0. So this is nice because you can again see how the algebra agrees with the geometry. If they did not agree, there would probably be bugs somewhere, right? Okay. So there is one catch, however. What I said is actually not true. I can't say that the determinant is the area exactly. There is one little trick to it. Does anybody see what's the trick when I close the door? What could possibly go wrong? Yeah? Uh-huh. There's a thing, is the negative area is weird, right? Area should really be positive, right? So let's think about it. What does it mean? When, or let's look at it this way. When is the determinant, if you are staying in 2D in flat line, when is the determinant negative? So let's think about it for a second. So when is, if we are in, again, 2D, okay. And when is the determinant of v1 and v2, those are my 2 2D vectors, when is it exactly negative? Well, let's start with dot product, right? We know what I have shown here is that the determinant is basically just, in 2D, it's just the dot product of 2 vectors, where the second one is just a rotated version of v2. So let's start by looking at, I think we had it at some point, right? But let's recall that anyway. So before we answer this question, let's take a look at when is the dot product of 2 vectors. Let's call them u1 and u2. When is the dot product negative? So let me try to draw it. So let's imagine that I just can put the u1 here to make it easier. So this is my u1. For what u2 vectors I will get negative dot product? Pointing to the left, right? So here, exactly here, if my u2 goes anywhere in this half space, I get the negative dot product, right? So here is negative. On this line, they are exactly orthogonal, right? Here is positive, right? Now, everybody, I hope, understands this. The determinant of v1 and v2 is almost the dot product of v1 v2, except that it's a dot product of v1 and the rotated version of v2, where the v2 is rotated clockwise by 90 degrees. Let me write it here. Clockwise 90 degrees rotation. Okay. So what does it mean? Let's try to draw the same picture for the v's. So if my v1 again is here, think about it as like one as the base of my triangle or parallelogram or something. So let's see for what v2s I will get negative determinant. So that means after I rotate the v2, I need to get the dot product negative, right? After I rotate it clockwise by 90 degrees. So let's think about it for a second. So which one do you think it's going to be? It's a little bit confusing because you need to rotate it here, right? Well, maybe let's look at a few examples that should make it clear. So if I have a v2 right here, I will get rotated here, right? So the dot product is positive, so that's fine. So these give me positive dot product. This quadrant. If it's here, what happens here? If I have a V2 here, my proposal for V2 is here. After I rotate it here, right? So still positive dot product, right? So it looks like that this entire region will have the determinant positive. If my V2 is exactly on the x-axis, then the determinant is going to be 0 because the two vectors are collinear and we get 0. And here in this bottom quadrant, let's see what happens. If I have some V2, for example, here, if I do clockwise 90 degrees rotation, I get V2 points here and I get negative dot product. So indeed in this bottom half space, I get negative determinant, okay? So what does it mean? It means, so how can you, if I give you two vectors v1 and v2, how can you tell if the determinant of v1 and v2 will be positive or negative? You can't obviously tell easily if it's 0, right? Because you just take a look if one is a scalar multiple of the other. From this picture, what would be the rule to determine if the determinant will be positive or negative? So I give you, like, let's take a look at it. So let's say this is my v1, this is my v2. Positive or negative? Positive, right? If I do this, if I do v1 and v2, is it positive or negative? Negative, because like you have to rotate this so that this v1 comes here, and here we go to the negative part. So the rule is, if the shortest rotation which rotates v1 onto v2 is anti-clockwise, then the determinant is positive. And if the rotation between v1 and v2, the shortest rotation that brings v1 onto v2, is clockwise, then the determinant is negative. So yeah, so if we want to just compute the area, then we need to take the absolute value of it. So one immediately useful thing, if I want to compute the area of a triangle, if I have v1, v2, and I'm interested in an area of this triangle, this area is TA, then I can compute it simply by taking 1/2 the absolute value of determinant v1 and v2. The absolute value just cancels the sign, so we don't have to deal with negative areas. Oh, by the way, if I just flip the order, so if I take exactly the same vectors, right? And just do v1 and v2, then I would go from positive to negative, right? So that's like the ordering thing. But sometimes it gets important. Is that clear? So that's basically the complete geometric picture of determinant in 2D. If that's clear, let's take a look at the 3D case just quickly now. We're not gonna go into that much detail. So what means determinant in 3D? So here I have 3 vectors, v1, v2, v3, which are all 3-dimensional vectors. And I would like to give some geometric interpretation to the determinant of the matrix whose columns are v1, v2, v3. So what do you think that is? Let me draw some like examples. So this is my v1, this is my v2, this is my v3. What do you think is going to be the determinant? So this time we are in space, not in flat land, right? So instead of areas, we will be measuring volume, right? And what do you think is the determinant in 3D? It's like a direct generalization of the 2D case. Now, I'm not gonna do all the derivation. That would be even more. That would be more painful than in the 2D case, where it's relatively simple. Nevertheless, it's true. Well, you can again do the parallelogram or whatever it's called in 3D, right? If we extend this to like essentially like a skewed cube, In this case, it's like a perfect cube because I made them almost orthogonal. So the absolute value of the determinant of this matrix V1, V2, V3 is the volume of the skewed box. The skewed box defined by the three vectors, just like here. Okay. What is the sign in 3D? What does the sign of the determinant tell us? Again, just like in 2D, this can become negative, right? And what do you think that's determined by? It's a similar sort of idea as in 2D, except that now we have 3D vectors. Any ideas? If I flipped any two of them, I would have to flip the sign, right? Again, you can connect what you know from algebra to geometry, right? Like if I said this is going to be V1 and this is going to be V2, I would have to flip the sign of that. So I would immediately get negative area. So how can I tell if I give you three vectors and I ask you what was going to be the sign of the determinant? So this time it's relates to the concept of handedness of a basis or coordinate system with like not necessarily orthogonal vectors. So the determinant in 3D determinant is going to be positive if these form a right-handed coordinate system, and negative if it's a left-handed coordinate system. And I guess the last thing I would like to, I don't want to go into that much detail. You could go into more detail here, but that's not what we want to do here. So if this is my V1, this is my V2, and this is my V3, if I want volume of a tetrahedron, then I can just compute it as 1/6 of the absolute value of the determinant of V1, V2, V3. 1/6 is because I can chop this cube. You can sort of think about it if you have good imagination. You can chop the cube into 6 tetrahedrons of equal volume. Just like in the triangle case, we had to chop it in two. That's sort of obvious, right? If you split it into, you get a triangle. In 3D, it's a little bit more tricky, but it's still true. It's 1/6 is the volume of a tetrahedron. And these things, by the way, these things are very useful when you will be doing, if you will go to phys-based or already been to linear finite elements, which are, or mechanical engineering, I think that's also useful. Linear finite elements essentially are tetrahedrons. And if your rest-pose of your material, or even in the continuous case, the negative determinant would correspond to inversion of your tetrahedron. So if I have a triangle and I'm deforming it around, it's like a triangle corresponding to some elastic material, and it started with a positive determinant, that's what you would probably start with, so with determinant 1, deformed by identity. And if it's deformed to something that has negative determinant, that's something that cannot possibly ever occur in nature. If you have like some sort of small blob of some elastic material, maybe if it's like really soft, maybe you can compress it to 0 volume, but you could never really invert it. That's just something that happens in like the mathematical model, but it couldn't possibly happen in the real world. Okay. All right, so that concludes what I wanted to tell you about determinants. And in the following, we are going to be using them. And the first use of determinants will be already in eigenvalues and eigenvectors. So that's the next very important topic we're going to look at. There's a number of motivations how I could motivate that. One of them is, if you remember the DCT algorithm, the transform coding from one of the projects. I think I sort of vaguely hinted that the DCT basis vectors, these cosine functions, they can be expressed as eigenvectors of a special matrix, of a Laplacian matrix. That's one reason why eigenvectors are useful. Eigenvectors have eigenvalues and eigenvectors insanely many applications. I guess the most famous, or one of the most famous one, is the PageRank algorithm. I think we'll do a project after we get a little bit further on this topic on that. So if you don't know, the PageRank algorithm is like the original Google algorithm for discovering most relevant websites. And it all starts with like a relatively innocent definition of, or innocent requirement for an eigenvector and eigenvalue. So let's take a look how an eigenvector and eigenvalue. So okay, maybe I should explain the terminology a little bit. Eigenvalue and eigenvector, they always come in pairs. So eigenvalue is a scalar, and its corresponding eigenvector is a vector, and they are like brothers, or they are like buddies, if you want to think about it this way. I guess as I'm already talking about this, I can also mention that the eigen is a word from German. I guess it was probably first some German mathematician who came up with this, and it means its own or proper or something like this. So it means like the proper value or proper vector of a matrix, or like sometimes it's called characteristic value or characteristic vector of a matrix. And in German, they have this habit that just like form words by composing different words. So this is like eigen. You can hear like some different eigen things. They were like eigenfaces algorithm, or eigenanalysis, or eigenmodes, and all sorts of eigen things. Okay, so let's go over the definition. So again, we are working with square matrices, this time real. We'll actually have to look at complex or actually it will make sense to look at complex matrices later. But let's start with just real matrices, and we will see where the need for complex matrices will arise. It will, trust me. So let's say we want to find a vector V such that A times V is lambda V. If we find such a vector V and a corresponding scalar lambda, so lambda is a scalar here, so that means in this case lambda is a real number, then we say that the V is an eigenvector and lambda is its corresponding eigenvalue. Okay, so that's why they are like buddies, because the eigenvector has its associated eigenvalue, and the other way around, eigenvalue has its associated eigenvector. Doesn't have to always be unique, but we'll discuss these subtleties later. First of all, think about it. What does it mean geometrically? Just this equation. What is A times V and what is lambda times V if you give it like a geometric interpretation? And A is an arbitrary matrix. I don't know what that is. It's a square matrix. So how would we interpret the left-hand side? A times V. Well, that's applying the action of the matrix on the vector V, right? I think we discussed in the 2D or 3D case that every matrix can be understood as some transformation. So it transforms the vector V to go somewhere else, right? Like a rotation would rotate the vector. Scaling would just make the vector longer. And the lambda V, well, that just means that's really, really simple, right? If I have V here, then lambda V just means scaling it, right? There's one important thing that I must exclude: zero vectors, right? You could immediately point to me that 0V could be an eigenvector. Well, that's not cool. So we need to say non-zero. Non-zero vectors V. It sort of makes sense if you, we finished the geometric intuition behind this. So what this V means, the V is on the left-hand side and on the right-hand side. It's the same V, okay? So what this V means is it's a direction, or it's a vector, such that when transformed by the matrix, gets transformed onto a scale version of itself. Okay? So the matrix maps every vector somewhere, and the eigenvector is such a special vector that the matrix maps it onto a scale version of the same vector. Okay? Maybe let's go like let's do a few basic examples. So if I give you a 2x2 matrix like this, it's very easy to come up with an example of eigenvector. Give me an example eigenvector for this matrix. Hint, any vector you can think about will be an eigenvector in this case. For example, 1, 0. What it's gonna give me is, well, it's gonna give me 2, 0, amazingly, which is 2 times 1, 0. Indeed, if this is my A, this is my B, this is my lambda, this is my V, all holds. Okay. Well, let's look at a different matrix. Let's look at this matrix. 0, 1, minus 1, 0. Oh, and by the way, indeed, the geometrically, what is this matrix doing? It's corresponding to some transformation, right? It's a very simple transformation. It's what? Just uniform scale, right? So it just scales. If I have something here, it just scales it twice, right? So indeed, like if I take this vector, it just gets scaled twice. So yeah, everything is cool here. This matrix, that's my minus 90 degrees rotation. I just took from the previous discussion. That's when we talked about determinant here. So will there be an eigenvector in this case? Or for any rotation in 2D? It's not going to be an eigenvector, right? So that's good thing to realize that the eigenvectors, they don't always have to exist, unfortunately. And that's actually the reason why we'll need to go to complex numbers to make them exist. But let's leave that discussion for later. So yeah, if you have a 2D rotation, there is no eigenvector here. The interesting thing is, if you go to 3D, if I look at the 3D rotation, would there be an eigenvector? And if so, what would that be? So again, think about it geometrically. It's a vector, so that when subjected to the transformation, it gets mapped onto a potentially scaled version of itself. This scale that can be anything except for 0. Oh, actually, no. The eigenvalue can be 0. Sorry, eigenvalue, it's perfectly fine to have eigenvalue 0. It's not okay to have eigenvector which would be all zeros, because in that case, this equation is saying nothing, right? We will ultimately want to be normalizing the eigenvectors, and dividing by 0 would not be cool. The other way you can look at it, what matters here is the direction of the eigenvector, right? If I have a vector which is 0, it doesn't have any direction, so that wouldn't make sense. That's why I need to exclude it here. So, rotation in 3D. What do you think the eigenvectors would be, just based on the geometric intuition? Well, let me give you an example. I could just take this one, right? That's the one which did not have any eigenvectors, just like any other rotation in 2D, and just extend it to a 3D rotation like this. Can you find an eigenvector now? So this is a 3D rotation in the XY plane, right? Totally cool. Well, I'm probably not going to succeed on the first two components, right? So what I can do instead is I can just try my luck on the last one. Well, let's see what happens. Well, it's quite obvious, right? I get 0, 0, 1. So if I put here a little 1, this is a perfectly valid eigenvector. So do you see, in general, if I give you a general 3D rotation, what is the eigenvector of that going to be?
Axis of rotation.
The axis of rotation, and the eigenvalue is going to be always 1. So here you can see again how it beautifully connects to geometry. And even without, I even didn't tell you how to compute eigenvectors in general. That's what we're going to do next. But you can already, from the geometric viewpoint, sort of reason about it and realize some interesting things like this. Okay, so how do we compute it in general? Like in these toy cases, you can just sort of hand wave your way through it, or just guess it. And in general, what you can, how do we compute eigenvalues and eigenvectors of a matrix in general? So first, I just put it all on the left-hand side, so I get this formula. This I is an identity matrix. This is just to make the types agree, right? Because I couldn't write there just lambda, because then I would get like a syntax error, because the A is the matrix and lambda is a scalar. So I cannot just subtract scalar from a matrix. I need to multiply by identity, but that's okay because identity times v just gives me v back, right? So it's just like a type sort of thing. what does this mean? I just subtract lambda from every element on the diagonal of A. Okay, so obviously these two equations are equal, right? And what does this equation say? It says that, what does it say? And remember, we need to be looking for a non-zero vector v. Okay, zero would trivially be a solution, right? So when the system will have non-trivial solutions, that's what's written here. But let's think about it. Because you already know that from what we talked about before. Well, it only has a non-trivial solution if there is a non-trivial null space of the matrix. Okay? And there is a non-trivial null space, non-trivial meaning more interesting than just the zero vector of dimension at least 1. And that's only going to be the case if this matrix is singular, A minus lambda I. Okay? Now what we just said about determinants, you can use the determinant to detect if it's singular or not, right? As we discussed on Monday, the determinant is 0 if and only if the matrix is singular. So for lambda to be an eigenvalue of matrix A, it must be true that the determinant of A minus lambda identity is 0. So this is nice because you sort of simplified the problem of finding eigenvalues and eigenvectors to just finding eigenvalues first, and that makes it easier, right? Because now I just need to worry about the single scalar. Once I have found the scalar, the eigenvalue, then I can think about how to find the eigenvector. Actually, that becomes simple, right? Because that's what you already know. So really, the hard thing here is to find the eigenvalues. Well, let's think how this can be done. Well, what is the determinant of A minus lambda I? From the big formula we started with, we call it here, you can notice that this is going to be a polynomial of degree n in lambda. So the lambda is the unknown here. That's what we are solving for. That's the eigenvalue which we don't know and which we want to solve for. Okay. The matrix is known. These A's, the elements of the matrix, that's what we know. Okay. And the matrix here looks like the A minus lambda I looks like this. Let me just write it in like 2 by 2 case, for example, ny1 minus lambda, a12, a21, a22 minus lambda. Okay? So I will at most hit exactly n lambdas. That will give me the degree n. When that's gonna happen? Well, when I'm doing the product of the diagonal terms, right? So you can immediately tell me what is going to be the coefficient with the lambda to n term. It's gonna be, can you see that of the polynomial? I think it's gonna be minus 1. We write it here, minus 1 to n, right? Because each of them has minus, and there's gonna be in general n of them. So in 2D there will be 1, in 3D there will be minus 1. So it's a polynomial, and this polynomial is very important. It's called the characteristic polynomial of the matrix. Again, because it contains a lot of information about the matrix. So let's make this more concrete by looking at an example. Let's try to compute eigenvalues and eigenvectors for 2 by 2 matrix. In the 2 by 2 case, the polynomial is going to be quadratic, so we can solve it relatively easily. Okay, so let's do that. So first we form the characteristic polynomial. So I subtract the lambda identity, and I take the determinant of that. Okay, so we can work out, now we have specific coefficients, so we can work out what exactly is the polynomial going to be, right? So first we expand the determinant, so this term times this term minus these two. And if we work through it, let me quickly check if that's really correct. So here we have, so this is the as I said before, this is n equals 2, so this indeed this term is lambda squared with +1 coefficient. And then we get 0.8 minus 0.8 lambda minus 0.7 lambda, so that's in total minus 1.5 lambda, so that's what you got here. And here we get 0.8 times 0.7, which is, if I'm not mistaken, 0.56, and from this we subtract 0.06, which gives us 0.5, so that's what you got here. Okay. So this is our quadratic polynomial, and if we solve for it, we find the eigenvalues. So you know the formula how to, I hope you know the formula how to solve a quadratic formula. So if I have, in general, if I have ax squared plus bx plus c equals 0, you probably remember this better than I do, right? So the two roots are the minus b plus minus the square root of b squared minus 4ac divided by 2a. Everybody knows that, I hope. This is the formula for the roots of a quadratic polynomial. So in this case of this polynomial, these roots will be the eigenvalues, and that's what we can do here. And if we work it out, if we just use this formula and substitute our actual numbers, so here the b is 1.5, so with minus it's minus 1.5, with minus it's 1.5, plus minus 1.5 squared minus 4.5, so here we get what? We get 3, 2 squared, which is 9 divided by 4. 9 divided by 4 minus 2 is minus 8/4, so that's in the end, that's 1/4. If I take square root, it's 0.25. Sorry, if I take square root, it's 0.5. So this is, so this gives me two solutions. Either it's, if I do 1.5 plus 0.5 is 2, so divided by 2 is 1, and the other one is 0.5. So here it was nice. I mean, I picked the matrix nicely to begin with, so I get nice eigenvalues. In general, you can get some ugly numbers there. This is only because it was a nice matrix. So this matrix has two eigenvalues, 1 and 0.5. Okay. Now, how do we find the eigenvectors? So in general, let's go back. So if we already found the eigenvalues, or let's just pick one of them. We do it one at a time. But one eigenvalue, how do I get the corresponding eigenvector? You should already know that from the previous part. So I already solved for, I already have the lambda, right? So I need to find the corresponding v for this particular lambda, which is non-trivial, which is not all zeros, that's forbidden, and it's in the null space of a minus lambda I. Well, what I need to do is look at the null space, right? If I find any non-trivial vector in the null space, and I'm done. So let's take a look. Take a look how it's done, how it looks like in our example. So we take this formula, we plug in the eigenvalue we just found. So let's start with 1. Okay. If we do that, we do 0.8 minus 1 here. So this is minus 1 times identity. So we get 0.8 minus 1, 0.7 minus 1. So that boils down to minus 0.2, 0.3, 0.2, minus 0.3, right? This is minus 0.2, this is minus 0.3. So notice that this matrix is singular. That's the whole point, right? If you are doing this calculation and you don't get a singular matrix, then you have a bug somewhere. You made a mistake somewhere. because that's exactly how we computed the eigenvalues, such that this matrix is singular. Well, and from this we can easily compute the eigenvector. Here I sort of just like guessed it, right? You can just flip the sign and the order and you get one of them. If you wanted to do it by the book, you also can. So one way to do it, you can just, because it's singular, you can just discard the second equation and you can just do 0.2x1 plus 0.3 x2 equals 0. You could say that the x2 is a free variable, so you can pick whatever. So you could say, for example, x2 is 1, why not? And that gives me x1 equal to minus 0.3 divided by minus 0.2, right? So it's 0.3 divided by 0.2, which is 1.5. So the corresponding eigenvector would be 1.5 and 1. And notice that these all are cool. Oh, by the way, do you know what is this symbol? What does this mean? It means it's proportional to. So I guess I could write it maybe better like this. Is alpha times, I guess that's why it looks like alpha in the first place, 0.3 and 0.2. Okay, so what this means is that the eigenvector is determined up to its magnitude. The magnitude of the eigenvector doesn't matter. All that matters is the direction. Okay, the magnitude doesn't matter as long as it's not 0. I mean, that's the whole point, right? Or you can look at it in terms of a subspace. The subspace is that's what's important. In this case, the one-dimensional subspace. The particular vector, if I pick 0.3 and 0.2 or 1.5 and 1, that doesn't matter, right? Or I can multiply this by any scalar, and it's going to be equally good eigenvector. Okay? Yeah, so that's exactly what's written here. And then, so now we found, so this is the eigenvector, whatever I want to scale it with, it's still going to be a good eigenvector, and it corresponds to the eigenvalue lambda equals 1. So that's the first eigenvalue. Okay? We can do the same thing for the second eigenvalue. So the second eigenvalue was lambda 2 was 0.5, right? So we can do the same thing for 0.5. So subtract it from the diagonal. 7 minus 0.5, we check. Yeah, 0.8, 0.3, 0.2, 0.7. So what is this matrix? This matrix is 0.3, 0.3, 0.2, and 0.2. Again, you can immediately see that singular. That's good. That means I did not make a mistake, and remarkably. So give me an eigenvector. An eigenvector, right? Because you can come up with infinitely many of them. So again, it's a vector which is in the null space of this matrix, right? So if I multiply the vector with this matrix, I get zeros. So what would be your favorite? 1, -1. That's my favorite too. Good one. Another good one would be -1, 1, right? But you could also say like 100 and -100, or 0.99 minus 0.99. It's defined up to a scale. So that's the second eigenvector, and that that concludes this. Now we have completely solved the eigenvalues and eigenvectors of this matrix. And I guess this thing, I don't feel like going to this today. Let me just give you a quick preview, and then we'll do it properly next week. Is that sometimes this process can fail, right? We already established that for 2x2 matrices, there is no such thing as an for rotations in 2D, there are no eigenvectors, right? So the process has to fail somewhere. Maybe before showing you this slide, maybe let me ask you, where do you think this could fail? Sort of. Yeah, that's a good thing to think about. if you code it up and run it on lots of random matrices, what's going to be the problem here? Where is it going to fail? So if I run this on a rotation matrix in 2D, it cannot possibly work, right? Because we just said that the eigenvector cannot exist. So at what point this algorithm will fail? Yeah? Exactly. Because what can easily happen is in this quadratic when I get the quadratic polynomial. Here I was lucky, right? Because I got quadratic polynomial. That quadratic polynomial always is some sort of parabola, or is a parabola. In this case, I was lucky because the parabola intersected the x-axis at 2 points, right? 0.5 and 1. So that was cool. That does not always have to happen, right? I can easily get a parabola which looks like this. Whoops. And no solution, unfortunately. And no eigenvector. Okay? And what do we need to do to fix that is to allow complex numbers as eigenvalues and eigenvectors. That's what we are going to do, but I think we are going to do it next time. Okay? Okay, so that's it, unless you guys have any questions.